Yeah, I'm very grateful to come to this place. In particular, when I see the Great Wall on the mountain, it's such a pleasant feeling. So I want to thank you for having this opportunity. So today, I would like to talk on some mass capacity related inequalities and their implications. The inequality I'm going to talk about next mainly modeled on two basic spaces. So I will first start with introducing these two spaces, which are rather basic. So the first one is the Euclidean space. R3 is a vector space with this standard metric. And the other model space is often called a spatial structured manifold, which I denote by M, a capital M with a sub M, lowercase m, and the metric G sub M. Capital M sub M is an open set in R3 where this function is positive. Now this function is a harmonic function with respect to the Euclidean metric, 1 plus m over 2 times the length of x. Now on this open set, if one equip a metric that's conformal to the Euclidean metric with this function raised to the power 4 as a conformal factor, and this metric is known as the spatial structured metric. As this conformal factor is a Euclidean harmonic function, then one sees that this metric has zero scalar curvature, and moreover, from the expression we see it's rotationally symmetric. All right, so these are the two model space which we are going to use later. Oops. Okay, next we'll recall the definition of an asymptotically flat three-manifold. The concept of an asymptotically flat manifold is in n dimension, but later in the talk, I'll mention why the content of my talk, why it's restricted in 3 dimensions. So a Riemannian three-manifold is called asymptotically flat if outside a complex set, it is diffeomorphic to R3 minus a ball. So that's on the topological aspect. On the metric aspect, the metric coefficient associated with such a coordinate satisfying this given decay condition. So it decays to the Euclidean metric in this described manner. Moreover, the scalar curvature of the metric is assumed to be integrable. So under these conditions, the limit at infinity, so this flux integral, this represent a large coordinate sphere. So if you let the coordinate radius go to infinity, this integral a priori is defined through the metric coefficient or the first order derivative of the metric. This limit exists and it was known as the ADN mass. So this concept was first proposed by Arnold Misner. It turns out this concept is indeed a geometric quantity. So it's actually independent on the choice of coordinates on which the metric satisfies these decay conditions. So therefore, it's indeed a geometric invariant associated to such a manifold. And that was shown by Barnick and independent by curvature back in '86. So this is the definition of the math of an asymptotically flat three-manifold, which is given as certain limit near the infinity. So it only depends, at least from the definition, it only depends on the geometry at infinity. And next, I will move straight to the to the concept of a capacity. So if Mg denotes a asymptotic flat Riemann manifold with boundary, the boundary we denote by sigma, then the capacity or the L2 capacity of this boundary surface is defined as the infimum of the Dirichlet energy of a function f, where f is 1 on the surface and f goes to 0 at infinity. So given such a function, you compute the Dirichlet energy normalized, and you consider the infimum of it. Now, because the manifold is assumed to be asymptotic flat, so near infinity, you can easily construct a barrier. And so in particular, you can see this equivalently can be characterized by a harmonic function which equals 1 at infinity and which goes to 0, which equals 1 on the surface, which goes to 0 at infinity. And you apply divergence theorem, you realize that this infimum is captured either by the Dirichlet energy of this harmonic function or integral on the surface. It's also captured by the coefficient of the leading order, by the decay term. And through this point of view, you have a very vivid physical interpretation of this capacity, because it's also known as the electrostatic capacity. So if you think, so take the classic case. Take the classic case where the manifold is R3. And you take this surface. You think this surface as a conductor in R3. So what this capacity is that you start to drop some charge on this conductor. If you drop a little bit amount of charge on the conductor, its potential will be raised a little bit relative to the infinity. So this capacity is that amount of charge you dropped on the conductor so that its electric potential is raised to 1 with respect to infinity. So heuristically, vaguely speaking, the capacity can be thought as a certain size of a surface observed from infinity or observed in reference to infinity. So given a surface, in R3, we have the classic geometric quantity. We have the surface area, we have the volume enclosed by the surface. But this quantity capacity, you can also think the measurement of some size of the surface, but from the infinity point of, from the point of view of infinity. So having said that, we could go back to the definition of the ADN mass. The ADN mass itself, by definition, is defined by data at infinity. And the capacity, if we take this heuristic point of view, is also somehow related to infinity. It's the size of the surface viewed from the infinity. Okay, by now I have, I think these are the main definition we need in this talk. Now, regarding one extra remark, thinking them as physical quantities, both the mass and the capacity, they have the unit of length in 3 dimensions. So they have the same unit of length. And as an example, if you take a round sphere in R3, then the capacity, according to this definition, takes the radius of the sphere. Okay, now coming back to the mass, a fundamental result concerning asymptotically flat 3 manifold. The mass of such a manifold is the Riemannian positive mass theorem. So in 3 dimensions, this was first established by Shen and Yao using minimum surface techniques, and later by Witten using spinors. So the theorem says if one has an asymptotically flat 3 manifold, the metric is complete, the scalar curvature is non-negative. Let's assume the manifold has no boundary for simplicity. then this condition would ensure that the mass defined earlier to be non-negative. And moreover, if it's zero, the m equals 0 if and only if the manifold is Euclidean space. Now, so this was, as I mentioned earlier, so it was due to Shen Yao in the beginning, and then proved by Witten, and then later in the past 2 or 3 decades, there is a sequence of work which also gives proof of this 3-dimensional PMT. So in 2022, Pengzi and Manon, along their work of the inverse mean curvature flow, so their work on inverse mean curvature flow also yields the proof of this 3-dimensional PMT. And in 2018, Li proved this theorem using Ricci flow in 3 dimensions. And more recently, based on intriguing work of Daniel Stern, Bray, Cadworth, Curry, Stern, they also proved the PMT, this theorem, using harmonic functions which approach a linear coordinate function at infinity. Also, Angustiani, Mazzuri, or Renzel, they give another proof of the 3-dimensional PMT using green functions. So, so now you can see, so at least in 3 dimensions, you have the minimum surface approach, the spinner approach, and then the weak inverse mean curvature flow approach, and the Ricci flow approach. And then these works are related to harmonic functions. And later you will see the inequality I'm going to talk also makes use of harmonic functions. So it's along the line of Bray, Cadworth, Curry, Stern, and Angustiani, Mazzuri, or Renzel. Right, so these are the, okay, so this is the basic, the fundamental result concerning the mass. Now, regarding, okay, before we move to capacity, one related inequality I want to mention goes back to Pengzi and Manon's work on the inverse mean curvature flow. So their work gives the following lower bound of the mass if the manifold has boundary. So if the manifold has boundary, the mass can be bounded from below by a quantity known as the Hawking mass under suitable conditions. So the work of Pengzi and Manon on weak inverse mean curvature flow imply the following result. If you have an asymptotic flat manifold with boundary, and the manifold has non-negative scalar curvature, so one assumes the boundary is area auto-minimizing, meaning that if you take another surface which encloses the boundary relative to infinity, and then the surface has no less area. So that means, so that's what this assumption that the boundary is area auto-minimizing means. And then in this general context, one still needs some, well, as far as I know, one also needs some topological assumption. Say in the proof of the Penrose inequality setting, one works with the so-called exterior domain, which are the region outside the outermost minimum surface. And in that case, it's known that the manifold is topologically R3 minus a finite ball. But in general, if you do not assume you are outside the so-called outermost minimum surface, then as far as I know, one still needs some sufficient topological assumption to guarantee that if you run the flow later will remain connected if you assume the boundary to be connected. So that's what I mean by the suitable condition. So you have a geometric condition which assumes the boundary to be area auto-minimizing, and then you needed a certain topological assumption to ensure the inverse mean curvature flow remains connected if it starts with a connected boundary. Then under these assumptions, the mass has this lower bound. So in this notation, this absolute value sign denotes the area of a surface, and H denotes the mean curvature of the surface. And moreover, you have the rigidity. if the mass equals the Hawking mass under these assumptions, then the configuration is Schwarzschild outside of CMC sphere. Right, so this is a major inequality relating the mass near infinity and the boundary. Now I want to move on to the setting where the capacity shows up. So if the boundary is non-empty, the capacity also relates to the mass. So if we recall the concept of the capacity, right? The capacity is kind of certain measurement of the size of the surface if viewed from infinity. One result, so the earliest result I'm aware of goes to Hilbray's proof of the Riemannian Penrose inequality in the general case. In Bray's work, Bray proved the following mass capacity inequality in the setting where the boundary is a minimum surface. So if you have a complete asymptotically flat manifold with non-negative scalar curvature with boundary, suppose the boundary is a minimum surface. And then the mass at infinity is bounded below by the capacity of the boundary. Moreover, the equality holds if and only if your manifold is spatial Schwarzschild manifold outside the minimum surface, which is known as the horizon. Bray's proof of this theorem made use of the three-dimensional positive mass theorem. In particular, you see this theorem doesn't assume much topological assumption. In another work, Dong and Song, they also made use of surface capacity in a very intuitive way in their establishment on the stability of R3 for PMT. So you can see that if the boundary is non-empty, the mass, the capacity of the boundary of the surface relates to the mass as well. In the rest of this talk, I'm going to discuss some other inequalities relating the mass and the capacity. So that's the plan of the remaining of this talk. Any questions so far? All right, let's start with one of the inequality of this type. So the setting here is analogous to the setting of the inverse mean curvature flow setting where one has a lower bound of the mass by the Hawking mass. So the assumption is one has given an asymptotically flat orientable three-manifold with boundary. Suppose the boundary is connected, and suppose the second homology of the manifold relative to the boundary is 0. So one assumes such topological assumption, and then assuming the metric has non-negative scalar curvature. And then one has the following relation or inequality involving the mass and the capacity. On the left side, it's m to the capacity ratio. We mentioned earlier that as two physical quantities, both the mass and the capacity, they have the same unit. They have the same physical unit. So therefore, their ratio is unitless. On the right-hand side, the Willmore functional, we know it's unitless. So here you have an inequality regarding to unitless quantity. And so this inequality also has the rigidity case. If the equality holds, the configuration equality holds if and only if the configuration is Schwarzschild outside a CMC sphere with non-negative mean curvature. Yes.
So when you have an electrovacuum configuration, so electrovacuum this capacity would be directly related to the maximum potential.
I don't know that. You're talking about
yeah,
like a papatopy,
Well, I mean, the static case.
The static.
Doesn't have to.
Right. Yeah. Yeah. I don't know about that. But I think one can compute it explicitly. Yeah, maybe this. Yeah, maybe this is something that's possibly related. So you may wonder why there is this half, the power 1/2 here. So on the model case, if you have the spatial Schwarzschild manifold, the so-called Schwarzschild manifold is also known as a static vacuum configuration, where you have the static potential. So if you compute this Willmore functional on the rotationally symmetric sphere, this quantity is actually the square of the static potential restricted to the surface. So therefore, if you take the square root of that square, so this quantity is, in that special case, in the model case, this quantity raised to power 1/2 is just the value of the static potential restricted to the surface. All right. So let me. Okay. So yeah. Okay. So I'm going to talk about some implications of such inequalities. The first, I'll mention that at the corollary, the three-dimensional positive mass theorem can also follow from such an inequality. In a similar way that if you have the previous inequality of mass, Hawking mass, which follows from the inverse mean curvature flow, then you can also derive the three-dimensional PMT. So here, using this inequality, one can see that the mass of one can also see the three-dimensional positive mass theorem. For example, you can focus on the special case where the topology is trivial. Say the manifold asymptotically flat is topologically R3, so you do not need to worry about the topological assumption. Then how to see the mass is non-negative. You can take a point. You can take a point and consider a small sphere surrounding the point. And then you apply this inequality, then you see this Willmore functional. If you take your sphere, for example, to be a small geodesic sphere, you have very well-known information on the expansion of mean curvature of small geodesic sphere. So you let the sphere become smaller and smaller. So that gives you the sign of the mass. Later on, we can talk about some other related implication. So this inequality too, indeed, it follows from another two inequality, which is the inequality 3 and 4 below. So the setting, so we have the same setting. Here, one wants that harmonic function to show up. So this U is the harmonic function which equals 0. In the definition of the capacity, we use the test function, which is specified to be 1 on the surface, which goes to 0 at infinity. Here, it doesn't matter that you take U to be the harmonic function, which equals 0 on the surface, which goes to 1. So for this harmonic function, you have these two inequalities. The first inequality has nothing to do with the mass. The first inequality says on the boundary, the integral of this Dirichlet of this gradient squared term cannot be too large if the Willmore functional is controlled. So in this setting, if you consider such a harmonic function, heuristically, the gradient cannot be too big near the boundary. It will be bounded by a local quantity, which is the Willmore function. So that's inequality 3. And moreover, you have a rigidity case. If the equality holds, if and only if it's a spatial Schwarzschild manifold outside a CMC sphere with non-negative mean curvature. And here you can see that the rigidity case only corresponds to the Schwarzschild outside a mean convex CMC sphere. Because say if you consider a Schwarzschild with positive mass, where say in a spatial Schwarzschild manifold with positive mass case, you have a CMC sphere and the reflection of it with respect to the horizon. These two surfaces, same Willmore functional, but infinity and asymptotic end. Then the capacity of this one is certainly bigger than the capacity of this one measured with respect to the infinity. So therefore, the rigidity case of inequality 3, it picks this mean convex one. Whilst inequality 3 has nothing to do, does not involve mass, we have another inequality which involves mass and the capacity ratio. So this one gives the lower bound of this ratio, also in terms of how big this gradient, the gradient of U on the surface. But for this one, its allows either case, even in this Schwarzschild configuration with positive mass. If you compute the both sides on either such a CMC sphere or that CMC sphere, you both get equality. Now, I mentioned that the previous inequality 2, which appears, if you view the capacity as a geometric quantity, then 2 would appear to be a geometric inequality. And this geometric inequality it's a combination. It follows from the combination of these two in a way that one just need to cancel this intermediate term, right? Because inequality 3 gives a lower upper bound of this term, and then inequality 4 really it gives a lower bound of this guy. So put them together and cancel that one, making the harmonic function seemingly disappear. Then one has the previous relation. On the other hand, this capacity is, by definition, is indeed encoded in that harmonic function U. So in that sense, the harmonic function U is still there, except it comes via this capacity. So, right, so now we see how inequality 2 arise from 3 and 4. And next, I want to talk a little bit about how they are derived. So I'll only give a very brief, brief outline of the proof of the previous slide, the inequality 3 and 4. So we notice that 3 and 4, they are modeled. Right? They have a model space of spatial Schwarzschild manifold outside CMC sphere. The way that these inequalities were initially derived breaks it to 2 steps. In the first step, one can obtain some analogous inequality, but with a model space of Euclidean space 3 minus ball. So in step 1, I derive some analogous inequality. So inequality seemingly to 3 and 4, but those inequality has a rigidity case that corresponds to R3 minus a round ball. Suppose you can do that, and then there is a general argument which can allow you to promote such inequality to a new type of inequality which has a rigidity case corresponding to the Schwarzschild configuration. So I'll first briefly explain this step 2, right? So step 2 is to explore such a conformal relation. So the observation first, was really given by Hugh Bray in Bray's proof of the Penrose inequality work. So the idea is whenever you have an inequality, which I'll just denote it by I. Suppose you have proven an inequality for a configuration MGU. So MG, in this case, our inequality involves U. So whenever you have an inequality for such a configuration MGU with non-negative scalar curvature, then you can consider a parameter V. Right? You take any harmonic function on this configuration, you call it V, and then you can conformally deform the metric. Then you consider the original metric G conformally deformed by this harmonic function viewed as a parameter, and then there is a related new harmonic function with respect to this metric. And then you can apply whatever you just derived in inequality I to this configuration, and then presumably you will get another inequality which I denoted by I bar. But in this case, this inequality will depend on this V. But now you have your freedom or flexibility in picking a V. So therefore, if you pick a V in a certain optimal way, you can promote whatever inequality you get here to another inequality with rigidity case corresponding to the Schwarzschild model space. So that's what I meant by this step 2. And that's from this the relation on these two models. And as I said, that was first used by Bray in his proof of the Riemannian Penrose inequality. All right, so that corresponding to this step 2. So now we can just focus on step 1, where one can try to establish some similar inequality like 3 or 4 with a weakened rigidity conclusion. And in that part, the main ingredients consist of the following two. First, one needs a way to detect the mass. One needs to detect the mass. And here, one needs a technical assumption on the decay of the metric. So in the definition of asymptotically flat, we see one usually assumes the metric decays to the second order. Assuming the metric decays a little bit more, one can show the following. If you consider that harmonic function u, which goes to 1 at infinity, if you scale such a quantity, so u inverse t denotes the level set, where t is the regular value. So consider this, you rescale it through this factor, and one can show it goes to 4 pi in general. And then you subtract it, and then you rescale again. You pick up a term that's m over the capacity. Now, in particular, this relation also provides a way to see why the mass is geometric, at least under this rather stringent metric assumption. So recall that at the beginning, I mentioned that the mass is a geometric invariant, which was shown by Barnick as well as by Crucial, earlier. Here a comment is, at least for such metrics, this relation also shows the mass is geometric, because why? such a harmonic function is geometric. It's 0 on the boundary, it goes to 1 at infinity. The capacity, this concept is geometric. So the mass is geometric as well. Yes.
What do you need to assume about the boundary gap?
Okay, for this inequality is really, really there is no assumption. So basically this relation, it can any surface homologous to the infinity, to a large coordinate sphere. So this is a local statement concerning the asymptotic flat end. Any other questions? Right. So here one is a way to find the mass, and then the other main ingredient again goes back to Stern's work, where Stern made this crucial identification of the scalar curvature to the level set of a harmonic function. In particular, Stern's work implies the following relation. So if you have a harmonic function where the two level sets are compact and they are homologous to each other, then really here you have an identity. So when we write this as an inequality, really I think it means it's an identity. So assuming if the gradient is not 0, then this really is an identity that holds for any harmonic function. In general, if you allow a critical point, then you write the relation as such an inequality. Now in three dimension, the Euler characteristic of each level set shows up here. So one want to use Gauss-Bonnet. So that's one reason that we were focusing on 3 dimension in this case. Another technical reason why we are in 3 dimension, at least at the moment, it also involves this limit identification. So even for this relation 5, as far as I know at this moment, one also needs to use the fact this is 3 dimension, partly because of the decay rate involved for the harmonic function. So in higher dimension, the decay rate of the harmonic function seems not enough to show the level set is sufficiently round. On the other hand, in 3 dimension, that seems to be okay. So these are the 2 major reasons why this talk is on 3 dimension only. So exploring this relation by Stern, then one can actually find that this quantity is monotone. And in the first step, you have this, you know that if this quantity, if let t goes to 1, you pick up the mass over capacity. So putting this together, you get some inequality, and with the case on R3 minus 4. And then you can apply the procedure I mentioned earlier. Then you can promote such inequality to get an inequality with rigidity case on Schwarzschild. There is some other monotone quantity here involving the mean curvature, but here is one of the most basic one, in my opinion, in the sense that it does not involve the derivative of the metric. Say for this quantity, it only makes use of the harmonic function as well as its level set. So one interesting question I think is whether one can use this to give to establish some mass inequality under certain weak regularity assumption. So that's something that might be interesting to have. So as I mentioned earlier, so here we give some brief outline of the proof of the inequality 3 and 4. And next, I want to proceed to the implication, the application of the previous inequalities. So first, I want to mention a result that goes back to an earlier result that Bray and I had. So let me first mention this inequality. So a corollary of 3. So let's recall what 3 says. So inequality 3 is this one. So under the previous assumptions on the manifold, if you look at this harmonic function, then you have this inequality 3, which has nothing to do with mass. But then on the boundary for this integral, it's natural to apply Holder inequality. If you apply Holder inequality, you pick up the integral of the gradient of u. But that term picks up, that term corresponds to the capacity. And then Holder inequality also gives you some term relating the area. So if you do that, you get a corresponding corollary. And that corollary, this relation 7. So in this relation, in this inequality, you compare the capacity to the area. So recall that the capacity can be viewed as a certain way of measuring the size of the surface, but with respect to infinity. The area is completely local. So here, if you compare these two, you have an upper bound. So such a ratio is always bounded by this right-hand side involving the Willmore functional. And moreover, you have the equality, the rigidity case. So as I mentioned earlier, this inequality was first found by Bray and I using Huisken-Immanen's inverse mean curvature flow method. Here one observed that it also follows from inequality 3. One reason I mentioned this inequality 7 is because it helps one to compare. So to come back to compare the inequality 2 and inequality 1, which is something that I will mention next. So let's recall what are these two inequalities. Right. So inequality 1 is the classic relation relating mass to the Hawking mass of the boundary. So that's inequality 1. Inequality 2 is the mass capacity inequality that we mentioned earlier. But here, to make a comparison, I'm going to throw the capacity term on the right. Yeah, so these are 1 and 2. So now we can have a comparison of them. So first of all, if you recall the statement of both inequality, they both need certain topological assumption. So modulo the topological assumption, let's move on to the geometric aspect. If the boundary has the Willmore functional, so the integral of the L2 norm of the mean curvature, if it's less than 16 pi, then we can go back to this relation 7, which is the one that's on the previous slide. So here, you move the area to the right, and then assuming this quantity is less than or equal to 1, then you multiply both sides by 1 minus this square root. Then the inequality flips the sign. So if the, in other words, in terms of the so-called Hawking mass, if the Hawking mass of the boundary is non-negative, then you have such a relation which follows from inequality 7. And in this case, assuming the area is assuming the boundary is area outer minimizing, so you have the mass greater than or equal to the Hawking mass, but this part of this relation really says the Hawking mass is greater than or equal to this quantity. So in this scenario, you see a relation between 1 and 2. So if the Hawking mass is non-negative and the boundary is area auto-minimizing, then inequality 1 is better than 2. In the meantime, if the integral of the mean curvature square is greater than or equal to 16 pi, again, if you go back to the previous inequality on the capacity and the area radius, then you see you get the opposite relation, the opposite inequality. And in this case, inequality 2. So you have such a sequence of comparison. The first inequality is inequality 2, and you see in this case inequality 2 is better than inequality. It's strong. It implies inequality 1. So you have these two scenarios. So it depends on your application and the information you have, I guess. So if you know a priori that if you have a control on the integral of the mean curvature square. So in particular, if you think physically, you know already that the Hawking mass of the surface is non-negative, as well as you know the surface is area auto-minimizing. Then of course, from this comparison, this Hawking mass, give you a better lower bound of the mass. Okay. On the other hand, if you are aiming at knowing whether the mass has a sign, so if you want to know whether the mass is non-negative or not, in that scenario, if you have this information already, then either inequality will show the sign of the mass right away. If you know, say 1 is greater than or equal to this normalized Wilmore functional, then either inequality give you the sign of the mass. Now you are left with the case where presumably the Wilmore functional is big. Now in that case, this relation seems to show that maybe it's better to work with this mass capacity inequality if you are hoping to get a sign of the mass. So I will illustrate this in the rest of the talk. Okay, so next, the implication I want to focus on of these inequalities concern the following configuration. So let's assume the manifold is asymptotically flat on one end, and heuristically near the other end, we do not assume any information. So the metric could be incomplete or could be complete. So here you have one end. Also, for simplicity, let's just focus on the simplest topological scenario, say R3 minus a point. And in that setting, so G is a smooth metric on R3 minus a point. Assuming G has non-negative scalar curvature, assuming the metric is asymptotically flat as x goes to infinity, no assumption is imposed on the metric as x approaches the coordinate 0. And okay, so maybe it's good to draw a picture again. So M is 3 minus point. So for this special configuration, one can consider all the surface that's homologous to a large sphere at infinity. We let S denote such a set of all closed connected surface that's homologous to a large sphere at infinity. And given any element in this set, we can consider this normalized Wilmore functional of the surface. And then one has the following observation. If you have a sequence of surfaces in such a set, so if you have a sequence of surface, each of which is homologous to a large coordinate sphere at infinity, and if along the sequence quantity, the capacity times 1/2 of the Willmore functional. If this product goes to 0 along this sequence, then the mass will be non-negative. This would be a direct corollary of this inequality too. Right? And that's because I think we mentioned this earlier. If you know somehow that the Willmore functional is less than or equal to 16 pi for any one of such a surface, then the inequality shows the mass is greater than or equal to 0 right away. Suppose not. Suppose along the sequence, every surface has relatively large Willmore functional, and then this assumption also implies the capacity itself goes to 0. So now both those two terms goes to 0. So you have the capacity and the capacity multiplied with the 1/2 of the Willmore functional. Both quantity goes to 0. So therefore you get a sign. So this is just a direct consequence of equation 2, of relation 2. In particular, this observation does not allow you. I mean, it's a statement that holds for any sequence of surface. In particular, it doesn't have to go to that coordinate singularity. So next, it makes sense to say, okay, let's focus on the sequence of such a surface which approaches the seemingly singular point, which corresponds to the coordinate x equals 0. Okay, now if we focus on such a sequence, sigma k. So here by this sequence, sigma k, we mean sigma k encloses the next one, and all of them approaches x equals 0. So for such a sequence, you can actually show that this property that along this sequence, this quantity goes to 0, it's actually a local property near the coordinate x equals 0. So recall that the capacity itself, by definition, does involve the asymptotic infinity, by definition. But here the observation is this claim that this quantity goes to 0 along such a sequence. This property has nothing to do with infinity. It's actually it only concerns what happens near x equals 0. And precisely, it's this proposition. So here sigma tuta is any chosen surface. So if you choose any sigma tuta, okay, you fix it, and then for large k, sigma k will be enclosed by sigma tuta. And then you can talk about a so-called relative capacity. So you can go back to the definition of capacity, but then you take this conductor or this surface as your reference. And then you introduce a harmonic function, which is 0 on sigma k, which is 1 on this fixed surface. And then such a statement, such a claim really follows from the maximum principle for harmonic function. All right, I mean, okay, now you see the condition you observed earlier. So such a sufficient condition for the positivity of the mass actually is a local property near the place which the metric presumably could be singular. So now you can put them together. You can write down an observation. So here is the corollary or a result of this type. So let's consider the manifold is R3 minus a point. Say near the coordinate singularity x is 0. Assume the metric is isometric to a perturbation of some model. So the model metric we denote the model metric by G bar. Say the model metric is in this setting. The model metric is defined on a small interval times S2. And let's assume the model is dr squared plus ar squared times a given metric on S2. So that's the model metric G bar. Now now one want to impose certain assumption on your perturbation. So the first assumption is you want to assume your physical metric is like a L infinity equivalent to your background model metric. So that's what this second assumption means. So really, under this assumption, you can go ahead to compare the capacity of the surface, compute it with respect to the model metric, and compute it with respect to the physical metric, if you assume those metrics are L infinity equivalent. Because by the definition of capacity, only the C0 information on the metric is involved. So that's why this assumption is imposed. And then you have such a sufficient condition that implies the mass to be non-negative. This sufficient condition really it's two conditions, right? The first one, so assuming this limit is 0, because everything involved is non-negative. So this limit equals 0 is equivalent to this guy equals 0. So this term as r goes to 0 is 0, and then this term, so this coupled with that goes to 0 as r approaches 0. Now this term goes to 0, so that's a condition that concerns what the model metric needs to be, right? So this quantity times this one as r goes to 0. It only involves the model you are choosing. So if the model satisfies this sufficient condition, and then as well as if you assume the perturbation h is suitable in the sense of the second condition, and then by applying what we mentioned earlier, the implication, the corollary from proposition 1, 2, and inequality 2, then one has the sign of the mass. And here is an example. Here is an example. If we take this AR to be R raised to a power B for some constant, I think in the literature this is known as a RB Horn type of singularity. And then if you do this calculation, assuming your perturbation is, assuming this term is a big O1 term, then this condition 8 reduced to saying that if this power B is greater than 2/3, then the mass is non-negative. And one has the negative Schwarzschild example. For the negative Schwarzschild example, this B is precisely 2/3, but one knows the mass is negative. This is just an example of such a condition A. To finish the talk, we can go to the other setting where the coordinate, where this part may actually grow. So instead of representing a singularity, let's consider the other scenario. So one can okay. So in this set of surface, one can consider the infimum of the capacity. Let's denote it by this C and G. Now it's not hard to see that this infimum is actually realized by any sequence which drifts to this coordinate x equals 0. And this quantity is positive, it's strictly positive if and only if the manifold admits a harmonic function between 0 and 1, where u goes to 1 at the reference at infinity. Here, the positive Schwarzschild manifold, the Schwarzschild manifold with positive mass is an example. And a related theorem of Hubray is that if you have a manifold which is asymptotically flat, complete with two asymptotically flat ends. So in general, if you have such a configuration, and u goes to 1 at infinity, and u goes to 0 on the other asymptotic flat end, then Bray, in his proof of the Penrose inequality, he had a result which implied that the mass is greater than or equal to 2 of this quantity, which is the infimum of all surface capacity. So let's end the talk with something that's That's analogous to Bray's result. So coming back to this case, so on R3 minus a point, if you have a metric with non-negative scalar curvature, which is asymptotically flat at infinity, suppose such a metric support a harmonic function which goes to 1 at infinity, which goes to 0 near the other end. So here you do not assume the metric is complete. However, you assume from the function point of view, you assume the metric admits such a nice harmonic function. And then first of all, you can show this limit exists if you look at the level set of such a harmonic function where the level set approaches x equals 0. Then this quantity has a limit. A priori, it might be infinity. So if a limit exists, either as a finite number or possibly be infinity. And then you have such a relation. The mass at infinity is bounded from below by this quantity, the infimum of the capacity, together with this number. We know, well, okay, it's a number if this limit is finite. Now one may ask, what are some cases where this is indeed finite or maybe 0? Well, here is an example. So if the metric is indeed complete, if the metric is indeed complete, and say assuming the metric has bounded Ricci curvature, has the Ricci curvature bounded from below, then one can use Chen-Yao's gradient estimate. One can show that this guy is indeed 0. So in particular, if you put this together, you see a Bray's theorem also holds in this setting. So in other words, if you have two asymptotic flat ends, in particular the metric is complete, and the Ricci curvature is bounded below. So in particular, this quantity Lu is 0, and then you can use this relation. You have that bound of mass. Okay, I think I'll stop here. Thank you. Piotr?
So when you got a statistical data set, so we know that it could be Cauchy now, that's by various theorems.
Right.
But could you use your technique to prove that it's Cauchy?
Yeah. Right. You can get information on the level set of the static potential. If the surface is not the level set of static potential, then not much. But if it's a level set, yes, you can write down the corresponding a family of inequalities on the level set of a static potential in that setting. Yes. Right. So it's a vacuum static. The static potential is a harmonic function. It applies. Yeah, it gives you some control on the value of the static potential in terms of the mean curvature of the level set. Yeah. I thought about that. Yeah, but so far it doesn't seem to have. To me, doesn't have to have. I haven't seen a much application yet, but yes, that's a very potentially useful case. Yeah. Yes. Right. Yeah. Yeah, I mentioned this relation due to Daniel Stern. In high dimension, let's go back to that page. So in higher dimension, you have, so this term is the scalar curvature of the ambient metric. And then, then in dimension, this term is replaced by the integral of the scalar curvature of the induced metric on the level set. Yeah, that's one hurdle to go over, no, to get over in higher dimension. Yeah, one doesn't know how to deal with it. Okay, yes. Thank you.